All right, perfect. Well, hello everyone. My name is Benjamin Miquel. I work at the Dam Expertise Department of Hydro-Quebec. What I'll be showing a bit today is the hazard that we use for our rehabilitation project here at Hydro-Quebec, as well as how we calculate the flow response spectrum. So, just a second. All right, maybe just an overview of Hydro-Quebec. We're a company owned by the government of Quebec. Almost all of the energy we produce comes from water. We perform the generation, the transmission, and the distribution of electricity. We have around 700 dams, around 100 spillways, 28 reservoirs with a huge capacity of 176 terawatt per hour, and an installed capacity of 37 gigawatts. So this is just a small overview of Hydro-Quebec. I'll start out with a bit the particularity about the seismic hazard here in Quebec. So here you have a map of Canada. Quebec is located here in blue. What you can clearly see is that our seismicity here is very different from the West Coast. We don't have any subduction zones. It's more interplaque seismicity. So the consequence of that is that there's a lot more uncertainty on where the next big earthquake is going to happen. Another difference is that the intensity of the earthquake and the frequency of the earthquake is a lot less than in the western part of Canada and British Columbia. And a major difference, and we'll see a bit the effect, is that we have a low attenuation, meaning that an earthquake can be felt very far from its epicenter. This is mainly due to the Canadian shield, so very stiff rock under Quebec, which allows a propagation of the seismic waves very far from its epicenter. In British Columbia, there's less this aspect because, well, the crust is really crushed in all parts, so it attenuates very rapidly the earthquake motion. Another difference, mainly also due to the Canadian shield, is that we are dealing with an earthquake with a very high frequency content. So this very high frequency content causes mainly risk to very stiff structures like concrete dams. So now I'll speak about the dams that we have. The dams at Hydro-Quebec were mainly built in 5 generations. The first generation are dams built before 1940. You have here an example of Beauharnois located close to Montreal. The second generation is a bit more up on the St. Lawrence River. You have here an example of Manic 5. So those are dams built between 1940 and 1960. The third generation, or mostly our dams at l'Abbé James, are very productive dams. They were built between the years 70 and 2000. You have here an example of Robert Bourassa built in 1979. And the fourth and fifth generation are dams that we're finishing building right now. We're finishing La Romaine 4. Those are dams located really more at the east of Quebec here. So now if I superpose the seismicity in Quebec, you can see that mostly our first generation dams are located in the most seismic area of Quebec. And those are dams that were built mostly without consideration for seismic acceleration. So there's no really seismic design that were done at their original conception. Another particularity here in Quebec is that we are legally obligated to validate the seismic behavior of our dams every around 10 to 12 years using a hazard of 1 in 2,500 years. So this is a hazard that is provided by the Geological Survey of Canada. It's an entity inside the government of Canada, and they perform the hazard estimation using probabilistic approach as presented before. Right now, we're undergoing major rehabilitation project, especially for those old dams in the red box here. Just put some examples here. We're investing $750 million in La Centrale de Carillon, $600 million for La Centrale de Rapide Blanc, and we have a huge amount of project underway. Those dams have reached their lifespan, and so we're doing major work to upgrade the dams. Sorry. Okay, so as I mentioned, there's a high uncertainty mainly in the attenuation law, and there has been important changes in the new generation of hazard calculation by the Geological Survey of Canada. As I mentioned, so in the West, the attenuation law are well known because there's a huge amount of earthquake. In the West, we have no exactly located faults. We do not have any faults. And we have a huge propagation distance of the earthquake. So this map here shows you the increase in seismic hazard for the spectral acceleration of 0.2 at a site class C rock. You can see, so this is the increase between two generations, the 2015 hazard estimation by the Geological Survey of Canada, and the 2020, it's still preliminary values. So you can see that the increase is pretty small in the West, while in Quebec, we have a huge amount of increase. The Geological Survey started to see that the uncertainty in the mainly the attenuation law was not well accounted for, or was there was not that much uncertainty well accounted for. So this is mainly the reason why we have a huge increase in the predicted values for 2020. Where our old dams are located, we have a major increase. So that's what I mentioned. And if we do not account for this increase in our major rehabilitation project, well, this could lead to unsatisfactory performance at the next study imposed by our legislator. And so we will have to redo a retrofit in the 10 next years after the project. So this is really not where we want to go. You have here an example of the spectrum at bedrock, hard rock class A, 1 in 2,500 years at the dam Beauharnois. So the red curve here is the spectrum that is right now used as the version of 2015. And the blue one here, same hazard, but obtained by the new model from the CGC and estimated for the 2020 version. So again, a big increase in acceleration. So our new philosophy for seismic performance is that if we are to intervene on a structure for various reasons, aging, unsatisfactory performance, problem of functionality, and depending on the extent of the project and the seismic risk at the dam location, well, we're going to be performing a site-specific hazard study or be using the CGC hazard value. If the structure that we're replacing or rehabilitating is anchored on the crest of the dam, we're going to be performing a flow response spectrum. I'll speak more in details about this aspect in the later slides. And there's really two philosophies. If we're doing a rehabilitation project, so meaning the structure is going to stay there, but we're going to reinforce it, we're going to be doing an evaluation for 1 in 2,500 years. This is what is legally required. But we're also going to do a design for 1 in 5,000 and 1 in 10,000 year hazard. We're going to compare a bit the result and see about if we invest a bit more, what protection we can assist. The reason we're doing that is really we do not want to intervene for seismic reasons on the structure that we have just rehabilitated in major projects. If we're replacing the structure, for example, replacing the superstructure of a gate lifting on the spillway, well, directly we're going to be designing it for a 5,000 year or 10,000 year return period. So I'll speak a bit more about this aspect. How do we calculate the flow response spectrum? So a bit the definition of the flow response spectrum. Here you have an example. The curve, the acceleration that you can see in black here is mainly the acceleration that could be provided by a seismologist with a given return period, let's say 1 in 2 of 2,500 years. If you need to replace the superstructure, the lifting superstructure of the spillway, if you use this acceleration to design the new superstructure, while you're not accounting for the amplification in the spillway, the piers. You can see the difference between the black curve and the green curve here. This is at the crest of the spillway pier. There's a huge amount of amplification. So you're going to be designing your superstructure with a lower acceleration than really required if you're using the black curve. So what we want to do is take the earthquake provided by the seismologist and with a given hazard and amplify it to provide a new spectrum for the design of the new superstructure. How do we do this? Well, this is the global methodology. It's really a three-step approach. The first one, well, is the selection and the adjustment of the time series. Then we're going to be performing a numerical model where we're going to apply the earthquake at bedrock and retrieve the acceleration at crest where the new structure is going to be anchored. And from these acceleration, we're going to calculate the new design spectrum to provide to the firm that is going to be doing the design of the new steel structure. I'll go a bit more into the details. So the first part, the selection and the adjustment of the accelerograms. So the aim is to transform a historical record where we have no really notion about the return period associated with this record into a 1 in 2,500 years or up to a 10,000 year return period earthquake. Usually we use 3 historical earthquakes and selected from the database developed by Mike Wire. We have different criteria for selecting these earthquakes, mainly on the magnitude distance, so from the aggregation results. We also have to check the PGA over PGV ratio for the frequency content. Once we have selected the 3 historical earthquakes, we're going to be adjusting it as presented in the last presentation. I prefer to use RSP Match. It's a software developed by Norm Abrahamson. It uses added wavelet technique in the time domain. There's mainly 2 ways from transforming the earthquake so that it fits the design earthquake. There's a time domain technique and there's a frequency technique. The time domain, in my belief, doesn't disturb that much the earthquake. So at the end, you're getting an earthquake that still has its characteristics. So here is the example. The green curve here is the spectrum of the original earthquake. And the red curve is the design spectrum on which we want to fit the earthquake. So we use the wavelet technique. We add the wavelets into the signals. You can see the difference between the green, which was the original earthquake, and the blue curve here, which is the modified earthquake, so that it fits on the spectrum. You can see that the differences are not that huge. This is the displacement that has little effect on the displacement, which is a good thing. And we do this for every 3 earthquakes and for the different directions. Next step is the numerical model. We're using 2 types of model. Let's say a very simple model. It's a stick model. At Hydro-Québec, we have a software called CADEM 3D. So we can use it to build a 3D model of, for example, our spillway pier. And it's able to output an equivalent stick model. This is a very simple model, but it works very well. So every beam in this model has the same geometric characteristic of a slice that you take into the 3 models. So we have the same inertia, the same area, etc. Once this is done, we import it into SAP 2000. This is what the software we we use here for very simple analysis. And in this case, I had to add the effect of the bridge because it really affects the dynamic properties of the whole structure. For some other cases, we might go into a more complex models, 3D model. This is the Mercier Dam. We had AAR on this dam, so I built first a 3D model mainly to study the effect of AAR, and then I used the same model to output the flow response spectrum. We also performed some field validation of the dynamic properties of the studied dam. The reason for that is that there's a huge amount of uncertainty coming from the dam itself. It's usually they're old dam. There has uncertainty on what kind of intervention there was done in the past. For example, is the bridge fixed to the piers or is it free from the piers? So this is going to change the rigidity in the bank direction. Clearly, we have a huge amount of uncertainty on the rock flexibility. If you ask your geologist to give you some models for the foundations, he's going to say something around 16 GPa to 45 GPa. The two bound of this interval really changes the properties of the dynamic properties of your dam. There's been degraded mechanical properties. Well, there's a huge amount of uncertainty. So what we do here is that several years ago, we bought a velocimeter device. So it's a very, very precise instrument able to measure very small velocities. And we use it to do ambient vibration measurements. The way it works is that any structure is solicited by many ambient vibration, ambient noise coming from the reservoir itself. There's noise coming from the production, the traffic, etc. Some of this noise is going to amplify into the structure, and by recording at the crest, you're able to, with different operation, to kind of find your natural period. I'm saying kind of find because for some dams it's pretty easy, but for some other dams, you have a lot of interferences. Example here, you have the interferences of the superstructure, so you might get peaks coming from the superstructure or peaks coming from the piers. And this is one of the problems of having only one instrument up to now, is that you're not able to output the mode chip. Anyway, by taking many measurements in, for example, here in the superstructure, you are able to retrieve the peaks coming from the superstructure that you want to change from the peaks that correspond to natural periods of the dam itself. Once we treat the result of ambient vibration, we're able to validate. Usually it's more validation than a calibration, because usually we get the natural periods pretty well, except if we didn't model well the bank rigidity coming in this example from the bridge. Finally, while we apply the modified accelerations at bedrock, usually I use a massless foundation, so it's maybe not the recommended solution for validating the stability of dams, but with all the uncertainty in bedrock, I prefer to have this aspect a bit more, with a bit more less complexity, because I'm not able to control the complexity exactly. So we propagate the earthquake, we retrieve the acceleration on the crest of the piers. From these acceleration at every piers and for every direction of the earthquake, we calculate spectrums. Usually I calculate them for different damping ratio. This is more a concern for the firm that is going to design the new steel structure. And then we apply the recommendation, mainly coming from the nuclear industry, is to widen the natural frequency of the dam to account for its certainty. Clearly, by doing ambient vibration testing, this step could be, well, we take a 15% widening of the natural frequency. We could use a bit less, but it's also to account for the effect of nonlinear behavior of the dam itself, where the pairs could change a bit due to damage. So this is what I get at the end. So in conclusion, due to the high uncertainty, an important evolution in the probabilistic assessment of seismic hazards, especially in Quebec, Hydro-Quebec has chosen to over-design rehabilitated or new structures regarding legally imposed criteria. So instead of using one in 2,500 year return period, we're more going to be designing for 1 in 5,000 or 1 in 10,000 year hazard. The flexibility of the dam causes great amplification in the design spectrum for frequency close to its natural frequency. So this is, for example, an envelope I get. The natural period of this dam was mainly around 0.08 seconds. So I have a huge amplification close to these natural periods. So this is a 6 Gs, it's really huge. But if I design the steel structure somewhere around here with natural periods around here, well, it's not really going to feel the amplification caused by the dam itself. So this is what I'm putting here. Hopefully the appurtenant structure will be more flexible than the dam. It's going to be somewhere in zone B, but you have to really check the higher modes because higher modes of the superstructure will usually have little modal masses, but you're applying a huge amount of acceleration on those higher mode masses. You also have to check for rigid cabinets anchored at on the crest of the piers. As you can see, there's an amplification of the PGA, so the anchors of your cabinets should be checked using the amplified PGA. After very good results with 1 sensors for ambient vibration, we have recently invested in multiple ambient vibration sensors. The reason for that is mainly to output the mode shapes. Sometimes it's pretty hard to interpret the results coming from just 1 sensor, especially if you have a lot of different noise coming from different production equipment close to the measurements. So that's about it for me.